When you design and learn some classification algorithm, sometimes it is very difficult to define the performance metric. So people sometimes use confusion matrix, which is a single value to assess your clustering algorithm performance, but it provides some full table of your classification result like this. There are two clusters index. Let's say there is two class no and yes, and there is predicted class no and yes by some classification algorithm, and write down the numbers. Both true and predicted value are no. For instance, this true yes, but the predicted by no. True no, but predicted to yes. True yes, predicted yes. Let's say this is 81. Then total there are 9,667, 333. This will be 9896. This will be 104. Okay. So why we draw such confusion matrix instead of just counting the number of misclassified item over number of total number of data point? So this is called error rate. Error rate is very nice metric to understand your clustering performance. But in some cases, this is not enough to understand your performance, and especially in practice, just simple error rate cannot give you very nice measurement. Okay, why? So in this case, the true no class contain 9,667 data point. But yes only have 333 data point. So when you design some very naive and simple algorithm, it always make output no matter which input comes to you. It will naturally have error rate 333 over 967 plus 333. So this is 10,000, right? So this is 0.0333. This is pretty small, right? So when you look at this error rate, you can think, wow, this algorithm is pretty accurate and we have very nice algorithm. So yeah, we don't need to design any new algorithm. Let's use this. But in reality, no, this algorithm is pretty bad and very stupid strategy. This algorithm never see any input value and just provide output index no. So this simple error rate cannot clearly explain the real performance, especially such unbalanced case. The simple naive and very stupid algorithm cannot predict the yes index, right? And if the yes index is very important and very crucial thing, we have to design another algorithm that can predict the yes index very well. So in some case, we can increase this entry value, but naturally when you increase this value, this side value will decrease, and this side value decrease means there are some more misclassification with this type, right? With this type. So in total, the number of misclassified nodes will be bigger than 333. with much smarter algorithm, right? So that's why the just simple error rate is not good metric for classification task, especially when the number of data point is not well balanced over the classes, right? Okay, so there are some natural behavior between the entries of confusion matrix. So there are some symmetric properties. When you increase this type of element, then the symmetric correspondence will decrease. So when you decrease this type error, then the algorithm might increase this type error. Okay, so there are some trade-off. If you decrease the first type error, then you might expect some increase of second type error. If you want to decrease second type error, you might expect some increase of first type error. Okay, that is very natural behavior, right? Then how can we control the type 1 and type 2 error? So let's go back to LDA or logistic regression. LDA, we have some discriminant function, delta kx. The logistic regression, we have some score function or logistic function, zkx. And we naturally find the cluster index using argmin operator that minimize the delta kx or zkx. Okay, this is vanilla form. But we can introduce some constant to each cluster, dk. And using these constants, you can control the type 1 error and type 2 error on all error types. If you increase this value, then you will choose cluster K more often than other cluster index. If you decrease TK, then you will hesitate choose cluster K because this value will decrease the delta Kx, right? So this constant is a very nice trick to control the type 1 and type 2 error. Right. Essentially using this, we say this is threshold. You can control the type 1 error and type 2 error. When you increase the type 1, you have decreased type 2